Hello everyone. In this video, we are going to discuss the subjective questions that came in BStat BMath 2020. So let's start with the first question. So it says that if I is a root of the equation x squared plus 1 equals to 0 and omega be a root of the equation x squared plus x plus 1 equals to 0, then you need to construct a polynomial where that polynomial will have all integer coefficients and it will have one of the root to be I plus omega. So a very simple thing to do would be to take x equals to I plus omega, because finally you will be getting the root to be I plus omega. And now if we take I on one side and omega on the other side, and now we'll cube it because we know that omega cube is equal to 1, so that's why let's cube it. So x minus I cube omega cube, and now if we expand it, so we are going to get x cube minus I cube minus 3I x squared plus 3x I squared, and that is equal to 1. Now if you simplify, so you're going to get x cube minus, and now I cube is minus I, so together you're going to get plus I minus 3I x squared minus 3x, because I squared is minus 1, and so this is equal to 1, and so we get x cube minus 3x minus 1 equals to I 3x squared minus 1. And now you see that we need a polynomial with integer coefficients, but we have I here. So that tells us to square both the sides, because if I square up I, so I would get minus 1. Let's square both the sides. So x cube minus 3x minus 1 whole square is equals to I square 3x squared minus 1 whole square, and this is equal to x to the power 6 plus 9x squared plus 1 minus 6x to the power 4 plus 6x minus 2x cube is equal to, now I square is minus 1, so minus 9 x to the power 4 minus 6x squared plus 1. And now if you take everything on one side and simplify it out, so you are going to get x to the power 6 plus 3 x to the power 4 minus 2x cubed plus 3x squared plus 6x plus 2 equals to 0. And so this is your required polynomial, and it has one of its roots to be I plus omega. This solution was proposed by Rakesh Kumar, one of my colleague at ISI. I have also posted my solution on my website. You can go and check it out. The link is in the description. I'm posting the solution in my video because it requires much lesser computational power than my solution, but the two solutions have their advantages. Like here you are finding a 6th-degree polynomial, but in my you can find a 4th-degree polynomial with such property. And so here is the solution of question 1. Let's discuss question 2. So it says that let a be a fixed real number. Consider the equation x plus 2 whole squared, x plus 7 whole squared plus a equals to 0, where x is a real number. Now for what values of a will the equation have exactly one double root? So exactly one double root. So note this condition because many students made this mistake. So we'll be considering our polynomial g of x to be equals to x plus 2 whole square times x plus 7 whole square. Now you must know that when can a polynomial have exactly one double root? That is, if f of x is a polynomial and alpha is a double root of f of x, then the condition is that f of alpha should be equals to 0 and f dash alpha should be equals to 0, but if double dash alpha cannot be equal to 0, because if double dash alpha is equals to 0, then the multiplicity of the root alpha is at least 3. So then we have to differentiate g of x. So if we differentiate g of x, so g dash x is equal to 2 times x plus 2 times x plus 7 whole squared plus 2 times x plus 2 whole squared x plus 7, which is equal to 2 times x plus 2 times x plus 7 times 2x plus 9. And so g dash of x is equal to 0 if and only if x is one of these numbers, that is minus 7, minus 2 and minus 9 over 2. But we see that if alpha is minus 7, then not only like minus 7 is a double root, but also minus 2 is also a double root. But we should have exactly one double root. And so a cannot be equal to 0. And so these two are not our options. So then we should go for minus 9 over 2. And let's check what g of x at x equals to minus 9 over 2 is taking. So g of minus 9 over 2 is equal to 5 over 2 whole to the power 4. And so you see that if we subtract 5 by 2 whole to the power 4 from g of x, then at minus 9 over 2 it will take the value 0, right? At x equals to minus 9 over 2, and thus a should be equal to minus 5 over 2 whole to the power 4. So this is the only possibility for a. And so we are done with question 2. Let's discuss question 3, which says that you have two variable points a and b on the x-axis and the y-axis, and the line segment joining these 2 points is of length 2d and it's fixed, and c is the midpoint of that line segment, and P is a given point where some conditions should be met, like P and the origin are on the opposite sides of AB, and PC is a line segment of length D and it's perpendicular to AB, and we have to find the locus of P. So let's first draw the diagram. Now here you have this AB, so A is on the x-axis and B is on the y-axis. So you have the midpoint of AB as C, and we have a point P such that whenever PC is joined, it's perpendicular on AB, and obviously it's on the opposite side of this origin. So now if you take the point A to be x comma 0, and since the point B is lying on the y-axis, so let's take it to be 0 comma y. Now from the given conditions, that is this length AB is of length 2D, and so since we have taken our coordinate of A as x comma 0, so this length is of x and this length is of y. And so from Pythagoras theorem we have x squared plus y squared is equals to 4d squared, and the coordinates of C is nothing but x over 2 comma y over 2. And now if you find out the AB vector, so it's minus x comma y, and since PC is perpendicular on AB, and so we have the orthogonal vector to be y over root over of x squared plus y squared and x over root over of x squared plus y squared. And we know that x squared plus y squared is 4d squared, so if you take it out from the root over portion, so you get 1 by 2d y comma x. And so now if you want to find out the vector PC, that is nothing but its length is given to be d, and so it's d times the vector E, and so that is 1 over 2d times d y comma x, and that is 1 over 2 y comma x. And from here what we can get is the coordinates of P, and so the coordinates of P are the coordinates of C, that is x over 2 plus y over 2 and y over 2 plus x over 2. So this is the coordinates of P, the point P. And so that is x plus y over 2, x plus y over 2. And so from these given coordinates of P, we can say that the point is lying on the line y equals to x. And so since the point P is lying on the line y equals to x, so that means its locus will be a straight line. But again, it's not covering the whole of the line y equals to x, so a part of it. So then we have to find its minimum and the maximum. Now we have the condition, that is x squared plus y squared equals to 4d squared, and we have to find the maxima and minima of x plus y over 2. And now if you apply the inequality, that is RMS, that is root mean square inequality, greater than equals to AM, that is arithmetic mean, and so we get root over of x squared plus y squared by 2 is greater than equals to x plus y over 2. And so from here we get root over of 4d square by 2 is greater than equals to x plus y over 2. And so this is equal to root 2 times d greater than equals to x plus y over 2. And now we know that the equality occurs when the two variables are equal. So we get x plus x over 2 is equals to root 2 d, and so we get x is equals to root 2d. And so the y value will also be root 2d, and so the maximum value for x plus y over 2 is root 2d, and it is attained for the point root 2d comma root 2d. Now to find the minimum value of x plus y by 2, so let's take the help of trigonometry and let's take this angle to be theta. Then by the projection rule we can say that x is equal to 2d cos theta and y is equal to 2d sin theta. Now we have to find the minimum value of x plus y over 2, which is 2d cos theta plus sin theta by 2, and that is d cos theta plus sin theta. And what is the range of theta? As you can see, the range of theta is 0 to pi by 2. Okay, so since it has to lie in the first quadrant, so the range of theta will be from 0 to pi over 2. So theta is from 0 to pi over 2, and in this range, now let's multiply with root 2 and divide by root 2 cos theta plus 1 by root 2 sin theta, which is equals to d times root 2 sin theta plus pi by 4. Now theta plus pi by 4 is ranging from pi by 4 to 3 pi by 4. And now since theta plus pi by 4 is inside the open interval pi over 4 to 3 pi by 4, so we have sine theta plus pi by 4 will always be strictly greater than 1 by root 2. And so root 2 sine theta plus pi by 4 will be greater than 1. And so this x plus y over 2 will be strictly greater than d times 1, that is equal to d. And so the locus of P will be t comma t, such that t is strictly greater than d and lesser than equals to root 2 d. And so we are done with question 3. Let's discuss question 4. So you have a real valued sequence xn and limit n tends to infinity, n times xn. This sequence tends to 0. So you have to find all possible real values of t such that limit n tends to infinity, xn log n to the power t will also go to 0. So let's see how we can solve this. So the idea is simple, that is, first of all, you just multiply with n and divide with n. So since you have limit n tending to infinity, n xn is equal to 0. So, and since you have to work with limit n tends to infinity, xn log n whole to the power t, so it's better to multiply with n and divide with n. And now this part tends to 0. And so if we can show that the other part also tends to 0, then we'll be done. Now our goal is to show or find out those t's for which log n to the power t by n, this limit goes to 0. Now you can do this using L'Hopital's rule, but the fun of the problem ends there, and you don't get to know how the actual sequence is behaving. So for that we need to do some approximation. So I'll show you by some approximation and will push the limit to 0. Now I claim that for a greater than 0 and for all x greater than equals to 1, we have log x whole to the power a by x is lesser than equals to a to the power a by e to the power a. So let's see why that happens. D by dx log x whole to the power a by x is equal to a log x whole to the power a minus 1 by x squared minus log x whole to the power a by x squared, and that is equal to log x whole to the power a minus 1 by x squared times a minus log x. So at x equals to 1, as you can see, my claim easily satisfies, and also at x equals to e to the power a, the equality holds. Now this derivative is greater than 0 in the interval 1 comma e to the power a, as you can see here. So, and also it is lesser than 0 in the interval e to the power a to infinity because of this part. So if we see the behavior of our function, so that is at x equals to e to the power a, it takes the maximum value. So it increases and takes the maximum value, and then again it decreases. And so its maximum value is at e to the power a. And so our claim is satisfying. Now let's apply our claim. So let's take t to be any real number, and we choose a to be greater than maximum of t comma 0. Then as you can see, for all n strictly greater than 1, what we have is log of n to the power t by n. So this is strictly greater than 0, which is equal to, so let's manipulate this a little bit. So log n whole to the power a over n times 1 over log n whole to the power a minus t, and which is again lesser than equals to. So now I am again using my claim here, and so this is lesser than equals to a to the power a e to the power a log n whole to the power a minus t. And now we can say that this part tends to 0 as n tends to infinity. And so we can say that xn log n whole to the power t, which is equals to n times xn log n whole to the power t over n, tends to 0, because this is tending to 0 as well as this part is also tending towards 0 for all t in R. So this is our answer, and we are done with problem 4. Let's solve question 5, which says that prove that the largest pentagon in terms of area that can be inscribed in a circle of radius 1 is regular. So if we have a pentagon inside a circle, so let's not draw it regular. Okay, and so this is touching the side, and the center be here. Now let's join each of those vertices, and let's consider each of those angles as theta I. So this is theta 1, this is theta 2, this is theta 3, this is theta 4, and this is theta 5. And so if I can show that all those theta i's are equal, then I'm done. Now, as we know that the area of each of those smaller triangles is half times the radius, that is r, times r sine theta I, right? And now r is 1. So the area of, like, suppose this triangle is half r squared sine theta 1. But again, r square is 1, and so it's half sine theta 1. So the total area of the pentagon is half summation j going from 1 to 5 sine theta j. And now each of those theta j's are from 0 to pi. Now the sine function in this range, that is from 0 to pi, it's strictly concave. And so what we can do is we can apply the Jensen's inequality. So summation j going from 1 to 5 sine theta j by 5 is lesser than equals to sine. Now the summation goes inside, j going from 1 to 5 theta j over 5. And now you know that the sum of all those theta j's is 2 pi. So this is equals to sine 2 pi over 5. So now we have that the area of this whole pentagon is lesser than equals to 5 over 2 sine 2 pi over 5. And now the problem tells us that the pentagon should achieve its maximum area. So A should be equals to 5 over 2 sine 2 pi over 5. And the Jensen's inequality says that the equality is achieved when each of those theta j's are equal. And if each of those theta j's are equal, so that means 5 times, suppose theta 1 is equal to 2 pi, and so theta 1 is equals to 2 pi over 5, and similarly I can prove that all the others are also 2 pi by 5. And so since for all j, theta j is equal to 2 pi over 5, and so we have that the pentagon is regular. And so we are done with this problem. Let's solve question 6, which says that prove that the family of curves x squared over a squared plus lambda plus y squared by b squared plus lambda is equal to 1 satisfies dy by dx times a square minus b square equals to x plus y dy by dx times x times dy by dx minus y. Now for these type of problems, what you have to do is you have to see what has been given to be proved. So look at these two quantities here, and according to that, let's do our calculation. So first of all, what has been given to us, let's differentiate it. So let's differentiate this thing. Let's see what happens. So now the given relation is x squared by a squared plus lambda y squared by b squared plus lambda is equal to 1. And now if I differentiate this with respect to x, I get 2x by a squared plus lambda plus 2y dy by dx by b squared plus lambda is equal to 0. And now from here, if you just calculate out y times dy by dx, so you'll get it to be equals to, so take this part on the other side and just cross multiply. So you will get minus x times v squared plus lambda by a squared plus lambda. And now again, as I told you, now we need to work with these two quantities. So let's first work with x plus y dy by dx. Now we have y times dy by dx. So let's add x with it and see what are we getting. So if I add x with y dy by dx, I'm going to get x times 1 minus b squared plus lambda by a squared plus lambda, and that is, if you just simplify, it becomes x times a squared minus b squared by a squared plus lambda. Now again, so we have calculated this part. Now let's see what was the other part. The other part was x dy dx minus y. So for that part, what we will do is, so x dy dx minus y. So we'll just manipulate this. So since we know y dy by dx, so let's do divide with y. So x over y dy by dx minus y, and that becomes equals to, just put the value of y dy dx, so it becomes x squared over y times b squared plus lambda by a squared plus lambda minus y. And so if you just take out b squared plus lambda by y and the minus sign, so inside you will get x squared over a squared plus lambda plus y squared by b squared plus lambda. And since this value is given to be 1, so this is finally boiling down to b squared plus lambda by y. And now we have found out these two values and we just have to multiply them. And so x plus y dy by dx times x dy by dx minus y is equal to minus x a squared minus b squared by a squared plus lambda times b squared plus lambda by y, and that becomes equal to, so now you must go and see what you have to prove, that you have to prove that dy by dx a squared minus b squared. So let's take the a squared minus b squared part out and let's see what we have inside. So minus x by y b squared plus lambda by a squared plus lambda. And now if you go back and see what we had as dy over dx, so if you take y on that side, so you are going to get that value to be, this value to be equals to dy by dx. And so this is dy by dx times a squared minus b squared. And thus we are done with problem 6. Let's solve problem 7. So it says that consider a right angle triangle with integer valued sides where a is the smallest side and b is greater than a and c is greater than b, and so that means c is the hypotenuse and the lengths a, b and c are pairwise co-prime, and d is the difference of c and b, and also d divides a. So the first part we have proved that d is less than equals to 2. So let's go for the first part. So Now, since it's a right angle triangle, so the obvious Pythagoras theorem comes in, and c squared is equals to a squared plus b squared, because c is the hypotenuse. And so from here we have a squared is equals to c squared minus b squared. Why did we take a on one side and c square minus b square on the other side? Because we have c minus b equals to d. So if we factorize it, we are going to get c minus b times c plus b. And we know that c minus b is equals to d. So this is d times c plus b. And also remember that d divides a. So let me write down the two conditions. Okay, now let's proceed. So since d divides a, that also implies that d square divides a square. And so what you can say is that in this relation a square equals to d times c plus b, since on the left hand side you have d square, and on the right hand side you can see that here you can see only one d, so the other d must come from c plus b. And so from here it implies that d divides c plus b. And now, so c plus b is some integer multiple of d. So where k is some integer. And so also we have c minus b is equal to d, right? And so from here what we have is d plus 2b is equals to kd. So I just replace c here by d plus b, and so I get d plus 2b equals to kd. And so from here it implies that 2b is equal to k minus 1 times d. Okay, now what we have to prove is d is less than equals to 2. And so the obvious thing we can do is to show that there is no prime factor of d greater than equals to 3. So on the contrary, we will take that let there exists a prime p which divides d and it's greater than equals to 3. Okay, and now look at this relation. So if p is dividing d, which and p is greater than equals to 3, so that also implies that p divides b. So this implies p divides b. And so it implies that p divides b plus d. And as you can see from here, b plus d is equal to c. And so it implies that p divides c. But it was given that all those a, b, c's are pairwise coprime. And so we have the GCD of b and c to be equals to 1. But p is dividing both of them. And so there exists no prime factors of d which is greater than equals to 3. But that is also not sufficient, because now all the prime factors of d can only be 2, but there might be more than 1 2 in d. So if 2 to the power alpha divides d, where alpha is greater than equals to 2, now look at this equality. On the left hand side you have 2b, and on the right hand side you have k minus 1 times d. And in d you have at least two 2's. And so that tells you that on the left hand side the rest of the 2 should come out from b. And so this implies that 2 divides b. And that implies again, since 2 divides b and 2 divides d, so again 2 divides b plus d, which is equals to c. And again that's a contradiction, because the GCD of b and c can only be 1. And so we are done with part A. So the part B says that find all such triangles with perimeter less than 100. Okay, so with all these conditions on ABC. Now you see, we will take, now D is lesser than equals to 2, that we have proved. And so we will take two cases where D is 1 and where D is 2. So our case 1, that is D is equal to 1. And so from here, what we have is, now we know that C is equals to B plus 1 then. Okay. And then C square is equals to B square plus 2B plus 1. And also C square is equals to A square plus B square. And from here, if you just cancel out B square, so you're going to get A squared as 2B plus 1. And so this implies that A is odd. And so we can take A to be of the form some 2k plus 1 form. And now let's square A. So we have this relation A squared is equals to 2b plus 1. So let's square A. So we get 4k square plus 4k plus 1 is equals to 2b plus 1. And from there it implies that b is equals to 2k square plus 2k. And now again we have a equals to 2k plus 1 and b equals to, so here we have a equals to 2k plus 1 and b equals to this, so 2k square plus 2k. And then what about c? So c is b plus 1, and so we have 2k square plus 2k plus 1. And so the perimeter, that is a plus b plus c, is equal to 2 plus 6k plus 4k square, and which should be strictly lesser than 100. And so you can see that k going from 1 to 4 is satisfying, and obviously k has to be an integer because all these sides, they have to be integers. Also, you might say that why can't k be equals to 0? But if k is equal to 0, then this condition is getting satisfied, but not this. Then b is equals to 0 and the side length can't be 0. And okay, so then the corresponding, the triangles, you can just find it out for k equals to 1, k equals to 2, k equals to 3, and k equals to 4. So they are 3, 4, 5, 5, 12, 13, 7, 24, 25, 9, 40, 41. So we are done with our case 1. Now let's proceed to case 2, where D is equal to 2. Again, then C is equals to B plus D, where so D is 2, so B plus 2. And again, let's square. So b square plus 4b plus 4 is equals to c square, which is equals to a square plus b square. And this is equal to, so a squared equals to 4b plus 4. And now for this case, it follows that a is even. And so let's take a to be of the form some 2k. And now again, placing 2k in this equation, we get 4k square equals to a squared, which is equals to 4b plus 4. And so from this equation we get b, so divide by 4, so we get b to be equals to k square minus 1. Now here c is b plus 2, so c is equals to k square plus 1. And so again the perimeter becomes 2k plus 2k square lesser than 100. And now as you can see that k will range, so the values for which this inequality will get satisfied is k will range from 2 to 6. Now you might ask, like, why k is not equals to 1? Because if k is odd, first of all, so k odd would imply that b is even, and so a and b will have some GCD, but again they are co-prime, and so k cannot be odd, and so k is not equals to 1, 3, so no odd numbers. And also for k equals to 2, we have, if you calculate out a and b, so we have a greater than b, but again the given condition says that a is the smallest number, and so this k equals to 2 also cannot happen. So the only possibilities are k equals to 4 and 6, and the corresponding triangles are 8, 15, 17 and 12, 35, 37. And so if you take the union of all those triangles that we got in case 1 and in case 2, that gives us our answer for problem 7, and we are done. Let's discuss problem number 8, and this problem was from combinatorics, and this was the toughest problem in the paper, and we have made it more tougher and by generalizing the thing. So first let's understand the problem. So you have like a definition of alternating sequences. So a finite sequence of numbers a1 to an is said to be alternating if a1 is greater than a2, a2 is lesser than a3, a3 is greater than a4, a4 is lesser than a5, and so on. Or it might be like a1 lesser than a2, a2 greater than a3, a3 lesser than a4, a4 greater than a5. Now if you read like this, you won't understand anything, so we have to like visualize how things are happening. And the question is asking that how many alternating sequences of length 5 are there with distinct numbers a1, a2 till a5. And now those AIs can be chosen from 1 to 20. Okay, so this length 5, now we will generalize it for any length n. Okay, and we will like take any n numbers and we'll find that how many alternating sequences are possible with n distinct numbers. Okay, and then from any set you can take those n numbers. And now if you have n distinct numbers, suppose a1, a2, a3, so suppose I arrange them in increasing order, so a1, a2 dot 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 till an, and now I can write 1, 2, 3 dot 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 till n, and I can simply form a bijection where ai goes to I. And so since it's a bijection, so working with any n numbers is basically the same as working with numbers from 1 to n. Okay, and now coming back to the sequence, so if you see that, first of all let's start with a1, and it says that for this type of sequences, like a1 is greater than a2, so here is a1. Now since a1 is greater than a2, so we'll draw a2 below a1 to denote that it's smaller than a1. Okay, and then again a2 is smaller than a3, so a3 will be above a2, and we don't know about a1 and a3 whether like a1 is greater than a3 or a3 is greater than a1. So again about a4, so a4 should be lesser than a3, so it's coming down, and again we don't know about a2 and a4 whether a2 is greater than a4 or a4 is greater than a2, and then again going back to a5 above, and a5 is greater than a4. Okay, and so on and so forth. And so if you draw the whole sequence, it will be like this zigzag form, and starting from above, so it comes down and then goes above, and that's why these type of sequences are known as down up sequences. Okay, because it's coming down, going up, and then again coming down, going up, and so this pattern will repeat. Now coming to the second form, so let's start with A1, and A2 is greater than A1, so let's draw A2 higher above A1, and then again coming down to form A3. As you can see, A2 is greater than A3, and then again going up to form A4. So again A4 is greater than A3, and going down to form A5 as A4 is greater than A5. And so you see that this goes up and then down, up and down, and so these type of sequences are known as up down. So as you saw in the problem, we'll say that a permutation a1 dot 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 an of the set 1 2 dot 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 n is an up down permutation. So up down permutation if a1 is lesser than a2, and then a2 is greater than a3, and a3 is lesser than a4, and so on. And again we'll say a permutation of this a1 a2 dot 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 an from the set 1 to n, down up permutation if a1 is greater than a2 and a2 is lesser than a3 and a3 is greater than a4, and so on. Now in the problem it was asking like alternating sequences of length 5. Now we are working with length n. Okay, now we don't know from where we will take those n numbers. Like in the problem it said that you will be taking those 5 numbers from the set 1 to 20, but it's like first uh, once you choose those 5 numbers and then you see how many alternating sequences you can form those with those 5 distinct numbers, and then it will be similarly for the other 5 numbers as you choose them. Okay, so that's why we are working with n numbers, and we'll see how many alternating sequences are possible with them, and so we can generalize it. So first of all, if you note that if I have 2 sets where in one set we have those up down permutations, okay, and in the other set we have those down up permutations, and now if we form the mapping, now both the sets are finite. I mean they have finite cardinalities. Okay, and so if I form the mapping, that is if I take a1 a2 dot 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 an, a sequence, an alternating sequence there. So basically I'm taking an up down permutation. Okay, and I'll be taking it to n plus 1 minus a1 and so on till n plus 1 minus an, and this will give me a correspond one-to-one correspondence between the set of all up down permutations and the set of all down up permutations. And so since they are finite, they are having finite cardinalities, so 1 1 also implies that it's onto, and so these two cardinalities are the same. So then if an is the number of up down permutations of length n, and also the down up permutations will be of length n will be an, as they are equal, and so the total number of alternating sequences of length n is 2an. And now using the definition of this an, we'll try to make a recursive relation, and thus we'll try to solve the problem. Now if you consider a permutation that is an alternating sequence a1 a2 dot 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 an, so since it's a permutation of the numbers from 1 to n, so one of them will have to be equal to n. So let ak be equals to n. Now, why did we suddenly take this number n? Like, why are we suddenly interested in who is taking n? Because n is the maximum number, right? Out of 1 to n, n is the maximum one. And whoever will be taking that, the neighborhood points will be lesser than that. And that's why from there we can like understand the behavior of the alternating sequence, whether it's up down or down up. So let's see. So from here it implies that ak is greater than the previous one, k minus 1, as well as ak is also greater than the next term, so ak plus 1. Yes, now if ak is a1 or an, then the other point won't, like if a k is 1, then ak minus 1 won't exist, and if k is n, then ak plus 1 won't exist. Okay, fine, but now we'll consider two cases. So case 1, when k is even. So if k is even, then let's again go back to the diagram. ak minus 1, ak plus 1. And now notice that the whole thing is an alternating sequence from a1 to an. Now we'll consider a partial sequence of it. So from a1, starting from a1, we'll consider till a k minus 1. So if you look at this, then if as k is even, so k minus 1 will be odd. And so from starting from a1, we are considering till a k minus 1. Now the next term, I mean the previous term, a k minus 2 will be above, and then ak minus 3 will be below, and so on, and it will go on. But how do we understand that at the beginning a1 is starting from above or below? Now as we know that here we have odd number of terms, since k is even, k minus 1 is odd. So you see, start like from a k minus 1, if you go up, so a k minus 2, and so if it ends like going back, if it ends above, then you are going to have even number of terms, right? But if it ends below, then you are going to have odd number of terms. And so since you have odd number of terms, so a1 will start from below. Okay, and so then after that it will go up and so on. So this will be an up down permutation. Okay, and for the next one, like from a k plus 1 till dot 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 an, this sequence will be like from a k plus 1, it can't again go down because the whole thing is an alternating sequence. So from a k plus 1 it will bounce back to a k plus 2, and then it will go down and then go up, and this one will be an up down sequence because it's starting from a k plus 1, then going up and then going down, and so again this will be an up down sequence. Okay, now of length k minus 1, how many up down permutations do we have? According to the definition, if the length was n, then it's an. So if the length is k minus 1, it's k minus 1. And again here we have this length is n minus k. And so the number of up down permutations of length n minus k will be a n minus k. And now again similarly let's analyze for case 2 when k is odd. So coming to case 2, k is odd, and so let's again draw the diagram. So here we have a k minus 1, a k plus 1, and now again things would go up from here. So if we look at from a1 till a k minus 1, so now k is odd, so k minus 1 is even, and so now the thing would end above. Okay, if you go backward, it would end above. So A1 will be starting from above, and it will come down and then go up and finally end at AK minus 1. So this will be an down up sequence. And so how many down up sequences of length k minus 1 are there? A k minus 1. And now if you analyze the rest, that is from AK plus 1 till AN, now it's again the same. It's starting from AK plus 1, it goes up and then it will come obviously down and then go up. And so this is an up-down sequence. And so how many up-down sequences are there of length n minus k? So it's A n minus k. And now let's combine case 1 and case 2 to find out how many alternating sequences of length n are there. So the number of alternating sequences of length n is 2an, because the total number of up down permutations is an and down up permutations is an. So together total number of alternating sequences are 2 times an. And now if we combine case 1 and case 2, and if we sum that up for k starting from 1 to n, so first of all you see that for the first group we need k minus 1 numbers. Okay, and the number n is already taken by AK. So rest we have n minus 1 numbers, and from there we need how many numbers for group 1, that is k minus 1 numbers. So how can we like take it out? In how many ways we can do that? It's n minus 1 choose k minus 1 ways, right? And for each such choosing, you obviously are left with n minus k numbers, and that goes to group 2. Okay, for case 1 as well as case 2. And so it's n minus 1 choose k minus 1. Now we have like chosen numbers for the two groups, and now for the first group we can make such sequences in ak minus 1 ways. Okay, so there are ak minus 1 sequences, and for each such sequences we have a n minus k sequences for the second group. Okay, and that combined case 1 and case 2 together, we have this result, that is 2an is equals to summation k going from 1 to n, n minus 1 choose k minus 1, a k minus 1, a n minus k. And now you would like to know that when k is 1, then we have here a0. Now if you look at the sequence a1, a2 dot 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 an, when k is equal to 1, so that means a1 is n. So a1 will be above and then it will come down to a2 and so on. And so from a2 it will go up. Okay. And if we look at the sequence from a2 to an, then it's an up down sequence, because it's from starting from a2 it's going up and then it will go down and then and so on. So it's an up down sequence. And how many such up down sequences are there? A n minus 1, because this length is of n minus 1, so a n minus 1. And so since when k is 1, so this will be a n minus 1, and a k minus 1, that is a0, will be initialized as 1. And similarly, when we will have k to be equals to n, so that means the two extreme possibilities, that is in this case a1 a2 dot 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 an, so here an is n. So since an is n, so finally it's ending above, and so an minus 1 and so on. So as you can see that sequence of length n minus 1 can be made in n minus 1 ways. And now the next one, that is a1, will be equal to 1, because if you have only one number, with that number you can make only one sequence, and so a1 is 1. And now for our problem, what we have to find out is 2 times a5, right? Because like we need to find out that given any 5 numbers, how many alternating sequences can we make out of it. And so now we have to do some recursive calculations based on our recursive relation and the two initial conditions. So if we calculate out 2a2, that will be equal to 2 and a2 equals to 1. So similarly 2a3 will be 2a2 plus 2a1 square, which is equal to 4, and a3 equals to 2. I'm not doing a detailed version of this calculations, so as you can do it because you have got the relation, so you just have to plug in the numbers. So 2a4 will be equals to 2a3 plus 6 a1 a2, and that will give you 10, and a4 equals 5. And finally what we wanted, 2a5, is 2a4 plus 8 a1 a3 plus 6 a2 square will be equal to 32. And so if we have any 5 distinct numbers, we can make 32 alternating sequences. And now the problem was asking us to choose 5 distinct numbers from the set 1 to 20. So how many such 5 distinct numbers from 1 to 20 we can choose? It's 20 choose 5. And for each such choosing, we can make 32 alternating sequences. So in total, 20c5 times 32. And that's the answer, and we are done with problem 8.